Okay, so happy Thursday. I hope you're enjoying math class right now. I hope you're treating the substitute well. And we're learning today about right triangle trigonometry. If you notice, we're skipping all the way ahead to section 13. So let me just tell you what I'm expecting for you today. First of all, definitely, yes, you need to take notes because I will be checking those on Friday. This classwork, when you finish with the video, you should start on it. It's not homework. We are going to finish it tomorrow. So what will I be checking tomorrow? The notes. At the end of the period tomorrow, this is due, okay? So let's talk about our essential question. We are asking, how can I use trig ratios to solve right triangles? So first of all, we need to define trigonometry. This is something that you've seen before, but not since geometry. And here's the deal. When you have different size right triangles, so here I have 3 right triangles all kind of drawn inside each other. Do you see them? There's this really mini red right triangle. There's this bigger green right triangle, and there's this the biggest black triangle, but they all share the common angle right here of theta. And what mathematicians figured out, what geometry people figured out, is that as long as right triangles have a same angle like these do, then the ratios of their sides will always be equal. So take a look at what I've done here. The smallest triangle, I said, hey, if we look at the hypotenuse, the side across from the right angle, and if we compare that to the adjacent side, and I'll get into that, if I compare these two, it'll be exactly the same for a bigger triangle, and it'll be exactly the same for an even bigger triangle. So in right triangles, these ratios of the sides are always the same as long as I have the same angle. And so what we did is we defined some trig ratios, sine, cosine, tangent, and we have some other ones. So first of all, you should know an acronym, and that is SOHCAHTOA. This acronym is very helpful for you. It will define what the trig ratios are. So sine, we're going to write sine of theta, because remember, sine of theta, we say, is the opposite side over the hypotenuse. OH. Sine is opposite over hypotenuse. So what am I talking about? Okay, so here's our right triangle. We said that as long as this right triangle has some angle, it's going to have the same ratios of the sides as all of the other right triangles with this same angle. So mathematicians started naming the sides. We named the side opposite the right angle, the opposite side. We named the side adjacent to that angle, the adjacent side. So see how this is opposite the angle, this is adjacent to the angle. And then you know that the hypotenuse is the side hypotenuse. This is the side across from the right angle. So sine is comparing opposite and hypotenuse. It's making a ratio of the opposite to the hypotenuse. Okay, next, we have cosine. Cosine is adjacent over hypotenuse. So see how if you're memorizing SOHCAHTOA, it helps you to know. So cosine is saying, hey, I'm going to compare the adjacent with the hypotenuse. I'm going to make those sides a ratio. Finally, we have tangent of theta, which is, well, TOA. Tangent is opposite over adjacent. So it's comparing the opposite side to the adjacent side. Okay, so here are our first 3 trig ratios. Yes, you do need to have these memorized. Yes, you can memorize them with SOHCAHTOA. But there are 3 new trig ratios that I need you to know. The first one is called cosecant. Cosecant is abbreviated CSC, and if we remember to put it right across from sine, we can remember it's just exactly the reciprocal of sine. So sine is opposite over hypotenuse, cosecant is hypotenuse over opposite. It's the reciprocal of sine. Okay, the next one that might be new to you is called secant. Just like cosecant is the reciprocal of sine, secant, which is abbreviated sec theta, is the reciprocal of cosine. So hypotenuse over adjacent, since cosine is adjacent over hypotenuse. Okay, finally, the last one and the easiest one is cotangent. And this one, unsurprisingly, is the opposite of tangent. We abbreviate it cot. It means cotangent, and it is the reciprocal of tangent. So tangent is opposite over adjacent. Cotangent is adjacent over opposite. By the way, I'm going to give you a lot of information in this video. It'll be a little bit of a longer one since you're watching it in class, but don't be afraid to ask the substitute to pause the video, because I know I'm doing a lot here, and especially if any of you need clarification. This is a review section, and so many of you who took geometry last year might be able to answer each other's questions. So here are the trig ratios. Very important that you know them. The first three you can memorize with SOHCAHTOA. And then the last three, as long as you remember what order they're in, they're just reciprocals of the first three, okay? All right, so let's look at an actual triangle. So evaluate the 6 trigonometric functions of the angle theta. I probably need to draw a picture for you. Let's say that I have a triangle, and in this triangle, I know that theta is up here. Here's my right angle, and maybe I know the sides are 3, 4, 5. Now remember, the sine, cosine, and tangent, all they're doing is they're telling you specific sides to compare. So let's name those specific sides. 4 in this case is opposite because it's opposite to the angle theta. 3 is adjacent, and 5 is the hypotenuse. So remember, hypotenuse always across from the right angle. Adjacent, always right. It's the side right next to the angle. And now they're asking us, hey, please tell me what sine theta is. Please tell me what cos theta is. Please tell me what tan theta is. So remember, what this is really meaning is they're saying, hey, orienting according to the angle theta, what's the opposite side over the hypotenuse? Well, in this case, opposite is 4. And hypotenuse is 5, sine theta is just 4 over 5. Because remember, all the trig functions are doing is they're telling me what the ratio of the sides is. Okay, cosine looks at adjacent over hypotenuse. The adjacent side for this triangle is 3. The hypotenuse, again, is 5. So there's cos theta. Tan theta looks at opposite over adjacent. Mr. Gregory, how did you memorize these all so easily? Because I remembered SOHCAHTOA. Definitely remember that. Okay, so opposite over adjacent would be 4 over 3. But remember, I have these other weird ones. I have cosecant theta, and that's just the reciprocal of sine, so 5 over 4. I have secant theta. This is just the reciprocal of cosine, so 5 over 3. And I have cotan theta. This is the reciprocal of tangent, so 3 over 4. So if they ever ask you to evaluate the 6 trigonometric functions, this is literally what they're looking for. They're just looking at, hey, compare all the different sides and according to what they're named. Okay, let's move on to a slightly more complicated example. So if theta is acute and sine theta equals 4 over 7, find the rest of the trig ratios. Interesting. So what they're doing is they're telling me, look, since I'm saying sine theta, we're imagining some right triangle with an angle, theta. And they're telling me that sine theta is opposite over hypotenuse. Well, aren't they just giving me what the sides are called, or what the sides' values are? Because remember, all sine is sine is saying, hey, I'm comparing the opposite and the hypotenuse side. That's what sine is saying. So my opposite side in this right triangle is 4. See how this side is opposite the angle? So I know for certain this right triangle's that side is 4, and I know for certain the hypotenuse is 7. Why? Because that's what sine theta tells me. It tells me the opposite and the hypotenuse. Now it's asking me to find the rest of the trig ratios. So I'm going to eventually have to find cosine, I'm going to have to find tangent, but all of these have to do with the adjacent side. And the adjacent side is the one side that I don't know. So how do I find the adjacent side? Well, hopefully you remember the most famous theorem in all of math, and that is a squared plus b squared equals c squared. If you remember, a and b are the legs of the right triangle, so maybe we'll call this a, and maybe we'll call the adjacent side b. C is always the hypotenuse. So we can solve for the third side by plugging into the Pythagorean theorem. So a squared, 4 squared is 16. I don't know b squared, that's what I'm solving for. C squared, let's see, 7 squared is 49. Let's subtract 16 from both sides. So b squared equals, is that 33? And then I need to take the square root here. So b, it looks like, is square root of 33. And let's write that on our right triangle. Because remember, when I do the other ratios, I'm going to need to know the adjacent side. So, okay, now I know cosine, because I know the adjacent side. So cosine is root 33 over 7, the hypotenuse. Tangent is opposite, 4 over adjacent, root 33. Now, hold up. I have a square root on the bottom of my fraction. That's not allowed. How do I cancel it? Think about it. You remember this. If I multiply by the square root of 33 over the square root of 33, I'll be left with 33 on the bottom. Great. I canceled the square root, and I have 4 root 33 on top. So here are my first two trig ratios. Remember that cosecant is the inverse of sine. So 7 over 4. Secant is the opposite of cosine. So that's 7 over root 33. And I'm going to have to do this again. So when I multiply by the square root of 33 over the square root of 33, this gives me 7 root 33 over 33. Now, cotan is going to be the reciprocal of tangent. I could reciprocate this, but wouldn't that result in a square root being on the bottom? And I don't really want that. So let's reciprocate what tangent originally was before I kind of messed with it. If I reciprocate that, I have root 33 over 4. And that is, yeah, there's no square root on the bottom, so I'm good to go. All right, sweet. So I found the other trig ratios. How did I do it? Well, first of all, I made my triangle knowing that sine tells me the opposite over the hypotenuse. So I made my triangle, I just wrote it out. I found the adjacent side, the unknown, by plugging into the Pythagorean theorem. And once I knew that, I could find all of the trig ratios, because all they are is just comparing two sides to each other. Okay, we're going to keep moving on. Yes, there's more. Trig values for special angles. Do I need this? Yeah, I need this. Okay. Here's the deal with these trig values for special angles. I actually don't care about you knowing these. Let's get rid of them. Remember how I said that all of the triangles have the exact same ratios as long as I know what the angles are? So for a 30-degree angle, in geometry, you hopefully learned about some special properties about 30-degree angled triangles. And I don't know if you remember this, but hopefully you remember that there's an x over here, there's a 2x in the hypotenuse, and this is x root 3. Does that ring a bell, like, at all? I don't know. I'm hoping it does. So just like all 30-degree angles follow this format, therefore, I should be able to say what is the sine of every single 30-degree triangle. So I know that sine is opposite x over hypotenuse 2x. And so this is going to reduce or cancel to 1 over 2. In fact, every time I do these problems, the x's are going to cancel. So let's just take away the x's right now. This is just a 1. Okay, the cosine is adjacent over hypotenuse, so root 3 over 2. The tangent is going to be opposite over adjacent, 1 over root 3. Typically, we like to write this root 3 over 3, like I multiplied by root 3 on the top and the bottom to get the root 3 off the bottom. So this is what tangent is. Okay, now, if there's a 30-degree angle here, what angle do we know is here? Isn't that a 60-degree angle? So just like I know all the 30-degree angle ratios, I should also know all the 60-degree angle ratios. I just have to orient myself differently. Now, since I'm orienting to this angle, this side is the opposite, this side is the adjacent. This side is still the hypotenuse. So let's see what changes. Now when I do the sine, opposite is root 3 over, whoops, I'm plugging into 45, which I shouldn't. Sine is root 3 over 2. And when I do the cosine, it's adjacent over hypotenuse, so 1 over 2. Notice how these flip-flop, and that should make a lot of sense, because instead of looking at this angle, I'm now looking at this angle. I'm orienting differently, and so the opposite side is going to be exactly the opposite one, if that makes sense. Likewise, the tangent is going to kind of be flip-flopped. So now instead of 1 over root 3, because my opposite and my adjacent switched, it's root 3 over 1. Let's simplify that to just root 3. Nice. Okay, now, just like there are special 30, 60, 90-degree triangles, there's also special 45, 45, 90. You're welcome for the amazing picture. 45, 90 go like this. Again, I don't know if you remember this from geometry. But there's, oh, I have a chance now. Redemption to draw a better triangle. I don't think it really worked though. Anyway, it's always x, x, x root 2. Now, just like this one, I knew all the x's would kind of cancel because I'm putting them into fractions. Let's do that here. Let's take away the x and turn these x's just into 1, because all 45, 45, 90 triangles will obey these general side ratios. So which one do we want to orient to? Let's orient to this one. It doesn't really matter because both of these sides are the same, but here I'm calling this one the opposite, here I'm calling this one the adjacent, here I'm calling this one the tangent. Okay, so sine opposite over, this isn't tan. Guys, it's time for a break. It's just time. All right, opposite over hypotenuse. Also, this is like the longest video ever. I'm just droning on, and I'm realizing now that when I upload this to YouTube, I'm gonna have to have my mom send me a special confirmation code because like it requires a text message and they never text it to Morocco. I don't know why I'm telling you these things. All right, sine we know is opposite over hypotenuse. 1 over root 2. Let's multiply by root 2 on the top and the bottom. That'll turn it into root 2 over 2. Isn't the cosine exactly the same? Because look, cosine adjacent over hypotenuse, that's also 1 over root 2. So let's write root 2 over 2 here as well. And again, the reason cosine and sine are the same is because look, they have exactly the same opposite and adjacent. Nifty. Tangent is opposite over adjacent, 1 over 1. And as we know, that reduces to just 1. All right, so again, don't worry about the cosecant, secant, and cotan. All we have to do is reciprocate. Just worry about sine, cosine, and tangent here. And we're good. Duh. Let's skip example 3. I'll teach this to you on Friday. This video has gotten long enough. The main takeaway is this. It's these guys. If you know how to get these guys, if you have memorized that, hey, the sine is always the ratio of the opposite to the hypotenuse, you'll be in really, really, really good shape. Okay, that's all I have for you today. At this point, pull out your books. Because you brought your book today, because you didn't think you would be doing nothing in class, because I told you you would be doing something small, pull out your book and work on these homework problems. All right? See ya.